They are advertised as oven and microwave safe.
So why is a well-known type of bakeware shattering without warning?
NBC6's Alina Machado takes us inside a demo kitchen to get answers.
In kitchens across the country,
after a Pyrex baking dish explodes.
15 minutes in, it was just like kaboom. It was like a bomb had gone off.
Shards of shattered glass start this story.
Within 2 minutes, I heard of an explosion. That was like a pop.
Reports of a well-known brand of glassware exploding. Pyrex, the kitchen staple for more than a century now, manufactured by Corelle Brands, was originally made of a type of glass called borosilicate, heat-tolerant and less likely, experts say, to shatter. But somewhere along the way, and Corelle Brands won't say when, that recipe changed, and Pyrex is now made of the less expensive soda lime glass, a type of glass now under fire from hundreds complaining online, posting photos of shards of glass they say came from Pyrex cookware in ovens, microwaves, and on countertops. From Michigan, it sounded like a bomb went off in our kitchen. Missouri, exploded in her hands, cutting her on the wrist, chin, and under the eye. And Arizona, it exploded violently, glass literally everywhere. So scary.
Thermal properties, expansion and contraction of substances due to changes in temperature. By the end of this video, you should be able to explain the Pyrex glass problem, the explosion of the shuttle Challenger, the challenges engineers face in designing our cities to deal with extremes in temperature and the state change of water, and how some basic devices like thermometers and thermostats work. There's a series of videos that I've posted that I would like you to watch that will help bring this alive and allow you to identify things we've done to control or utilize thermal expansion in our world. You'll need to be able to explain the difference between heat and temperature, describe how most solids, liquids, and gases change in volume and length due to temperature, explain water's unique behavior and how life on Earth would not be possible if it behaved like most other materials, and a basic idea of how thermostats and thermometers utilize thermal expansion, predict what substances would be best in a wide regime temperature environment, identify and explain technology designed to deal with thermal expansion, explain how fire and heat are different using the formula CH4 plus O2 makes carbon dioxide and water. This last goal above is a requirement in grade 10 science, but you can easily do it in grade 9 science. However, I would never test you on it. Now, this seems like an awful lot of goals, but it's actually much simpler to understand than itemize. The key, first of all, is to understand the difference between heat and temperature. Heat is the total energy in a substance in joules. We can calculate the number of joules of energy stored in a hot cup of coffee. Temperature is a measure of the average speed of the molecules or atoms bouncing around in that. Two objects can be at the same temperature and have different total amounts of heat. For example, you open an oven, you can stick your hand into the air, which may be at 350 degrees Fahrenheit. You can grab a piece of bread, which may also be at 350 degrees Fahrenheit, and you can hold it barely, but if you bump into the metal walls of that oven, you will be horrifically burned. They're all at the same temperature, but they hold different amounts of heat. And this is the mystery of pizza burns. If you bite into pizza that is too hot, you never burn your tongue. You burn the roof of your mouth, because the top of the pizza contains hot liquids and the bottom is dry crust. So you can think of a tennis ball compared to a cannonball. Both could be fired at you at 100 kilometers an hour, but they're not going to feel the same at all when they hit you. Another example would be a transport truck at residential speed is really what we'd consider a low temperature substance, but with massive amounts of heat energy. So even at low speed, it might crash into a building and go right through. A motorcycle at 200 kilometers an hour has an enormous temperature, but not much total energy. So if it's slammed into the back of a transport truck, he might not even notice the thump from that motorcycle. The textbook covers this reasonably well, using an example like this, where the one beaker on the right side has twice as much heat as the other because it has twice as much water. You could also do this by changing substances in the two beakers. Why do substances expand when they're heated? It basically has to do with the random motion of molecules. They vibrate when they're hotter. The motion is random. This is not the case with wind, and it's not the case with sound. When they're in a solid form, they have such strong bonds between them, there's very little vibration of what we would call the lattice, the structure of the solid molecule. But when we go to liquid, the bonds get considerably weaker, right? They're not gone because a drop of water holds its shape, but they're weak enough now that there's quite a bit more vibration these atoms can do, and so they will spread apart more as they warm up. When you get to a gas, the bond strength is dropping close to zero, and so as they heat up, they're automatically going to take up more space, like popcorn popping. They will start flying all over the place. So a gas may expand thousands of times when it's heated, but a solid, you need specialized tools to measure the change in size of a solid when it gets hot. An obvious good use of thermal expansion is thermometers. We put a small bulb of mercury or alcohol, and as we heat it, it expands. And by keeping the tube inside really tiny, we can sort of amplify that expansion. So the size of the reservoir bulb at the bottom is many times bigger than the size of the little tube going up. However, we must not allow these liquids to freeze or boil. Their thermal expansion will change drastically when they change state. If you were to boil the liquid inside a thermometer, not only would it no longer read correctly, it would explode. If you were to freeze the thermometer, thermal expansion would change to such a tiny value you would never see it move again. So this gives us a temperature range. A mercury thermometer is no good below minus 35 because the mercury freezes, but an alcohol thermometer could go down to minus 80 before it freezes. If you plan to go lower than that, you cannot use either. You have to get specialized thermometers. And similarly, there's a high end. Alcohol boils by 70 degrees where mercury can go up to 500. Electronic thermometers do nothing of this kind at all. They sense infrared light or currents in wires. They don't use thermal expansion. So the thermal expansion thermometers are gradually disappearing from our world. You'll be able to tell your kids about them. How much can we actually see in terms of an expansion? How big is this effect? Well, for solids like steel, it's 13 times 10 to the minus 6 per degree. This is a factor of 13 millionths. Decimal 0.1 is a single percent. So steel is growing thousands of times less than 1%. It grows by 13 millionths of its size for every degree. So we're talking, if you take steel from the coldest day on planet Earth to the hottest day on planet Earth, the increase is many hundreds of times smaller than 1%. But amplified over a long length of steel, it can be enough to buckle the material if we've not allowed it creeping room to change its size. And you can see the outcome of that effect on some rails on a railway. So it's not much, but it can be more than enough to make that impossible for a train to go over. Here is a piston in a car engine. These are beautifully engineered devices that sit in your car engine and move up and down during explosions and keep the engine running. You will recognize this as a hypodermic needle. It is remarkably similar in design to a car engine. It consists of this outer cylinder, part of the engine block, and internal to that is a plunger or piston that moves up and down. Here, there are rings that seal it to prevent any liquids from getting by. In a car engine, instead of there being liquid here, there would be an explosion of gases that will drive this piston up and turn the crankshaft very similar to pedaling a bicycle. This is what an actual piston looks like. Where you see the black rings in a hypodermic needle, on a piston we have these zones here to put in a seal. Now this piston has to seal to the cylinder walls very tightly to prevent explosions from getting by. And because of the heat they're exposed to, the pistons will expand. So they sit inside the cylinder here, and they fit very tightly. And these car engine blocks are high precision engineered devices to extreme tolerances. As a typical piston, you might fit to 0.01 millimeters of the cylinder wall. That's 10 times smaller than a human hair. So tiny changes in the size of this engine block during heating could cause the piston to grow and stop moving and destroy the engine. It's quite catastrophic when it happens. What would an engineer then want to make the engine out of? Well, typically they're made out of steel. And you might go, could we make a car more fuel efficient by switching to a considerably less dense material like aluminum? Aluminum is easier to work with, and it's vastly lighter. You could save huge amounts of weight by changing the engine from steel to aluminum. But if we look at the thermal expansion coefficient, don't worry about the per degree times 10 to the minus 6. Let's just look at these numbers. That normal glass expands a factor of 9 when it's heated, where silver expands a factor of 18 when it's heated for every degree. Look at the expansion factor of steel. It's 13 millionths per degree, and aluminum is 24. This means if you just change the engine block from steel to aluminum, things are going to expand twice as much upon heating. So that means you're going to have to make the piston fit with double the amount of space that it originally had around it. And that's going to make the engine rattle, and it's not going to work as efficiently. So aluminum was a tricky thing to get working for engine blocks. They have to play with mixtures, adjust for the fact that the heat expansion is different. And there were some disastrous attempts to make parts of the engine out of aluminum and other parts out of steel, and they would quickly warp and change. Now, if we go back to the Pyrex, we see the same thing with glass here. If you use normal glass, its expansion isn't terribly different from steel. It expands a reasonable amount. But if you start moving to these borosilicate glasses with lots of other chemicals, you can get it expanding to less than half what normal glass would do. That goes a long way to avoiding shattering, because it's when there's a sudden change in size, the thermal stress. One end of a glass is cooling and trying to contract, the other end is expanding, or it's not cooling as much, it'll shatter. You see this when you throw an ice cube in water. The ice cube tries to expand on the outside very rapidly. The heat didn't get into the center of the ice cube, which stays small, and the ice cube shatters. Glass will do the same thing. If you were able to switch to pure quartz glass, the expansion is so tiny now, you can take pure quartz when it's glowing white hot and throw it in ice water and it won't shatter. Now, why don't we make ovenware out of pure quartz? Simple. An ordinary glass cooking bowl might be $10. Proper Pyrex with borosilicate glass might be $30. If you wanted a pure quartz cooking vessel, it would be hundreds. Now, looking at these three types of glass, can you guess what form of glass would be essential on spacecraft? Would these windows be subject to high thermal stress as the ship goes in and out of sunlight at 90-minute intervals? And yeah, a lot. Even more so when the ships come back into the atmosphere. So these windows have 4 layers. They're made out of very low expanding glass, as low as they can get, and they're bulletproof. And then there's scratch proofing on them. There's a whole bunch of features they want. Where do you think the bulletproof layer is? Well, it would be on the outside because of meteor impact. So they have to try to engineer the windows to tolerate all the stresses of the environment they're in. And so this is a perfect example where engineers have to deal with thermal expansion and make sure these windows aren't going to shatter in flight, because these people would die. And they got to make it darn certain when they're in the dark side and the windows are extremely cold, if an astronaut went in there and was able to spill a cup of hot coffee, which there's no gravity, that the windows wouldn't shatter. Okay, and this is a very tricky engineering thing, so you're probably looking like at a ghastly expensive design here to make this safe for an astronaut to risk their life to get this kind of view.
Danger, danger, high voltage, when we touch, when we kiss.
Danger, danger, high voltage, when we touch, when we kiss, when we touch.
Danger, danger, high voltage, when we touch, and when we kiss. Danger, danger, high voltage, when we touch, when we kiss, when we touch, when we kiss. Perfect job!
So in recap, let's discuss how much science is inside this thing. First of all, you need electricity in order to create enough voltage to jump that air gap. Couple thousand volts per centimeter. This is a 10,000 volt transformer. And if I recall correctly, air is roughly around 3,000 volts a centimeter. So a 10,000 volt arc would be about 3 centimeters. And lo and behold, there's my 3 centimeters. So I'm not going to get it to work much wider than that. I have to play for a little bit to get that. So that spark, again, tells us it's fairly dry air, that it can't make that jump more than 3 centimeters. Now, once the spark jumps, the creation of ions provides a conductive path. Since the expansion of air when it's heated causes the air to rise, the ions drift upwards and the arc keeps climbing. And it gets to the top, and once it exceeds about that 3 centimeters roughly, it doesn't have enough voltage to keep the arc going, and it dissipates. Now, what causes the buoyancy in the first place? Well, the air expands, but without gravity, there wouldn't be any up or down. So in outer space, this device would just keep the arc at one spot. Well, how can I demonstrate to you that that would be the case? Well, if I turn it on its side, there isn't an up or down anymore. So I'm going to take this, and I'm just going to turn it that way, and there isn't really an up or down. And the arc just sits where it is. Okay? I can change the orientation this way. And the same thing, lacking the up or down, the arc has no reason to climb. And you are familiar with the fact that I keep saying there are no such thing as subjects. That there is no such thing as chemistry, physics, biology, engineering. They're all the same thing. This thing could occupy an entire course. Right? We've got metallurgy in there, conductivity, resistance, the formation of ions, the color of the light we see. It's all many, many, many subjects. We only bin them for your convenience. And what was this device originally intended for back when it was made? To light up neon lights outside movie theaters and other places. And in the meantime, I can do horrible things to hot dogs and pickles with it. Come on. Are you nuts?